Today we're going to be talking about Taylor polynomials and approximations. So it's actually kind of a fun lesson, I think, where we're going to be getting non-polynomials and we're going to be writing them as polynomials. So let's look at kind of a discovery activity that if you're in class with me, I would have taught you in class. We've gone through this in class. So I'm going to go through this fairly quickly because I want to get to some of the examples. So construct a fourth degree polynomial with the following end behavior. Use the fourth degree polynomial. Okay, so if I know p of 0 equals 1, p of 0, actually let me erase here. Apologize, I'm trying to be efficient. If I plug in 0, all those terms go to 0, so that gets me e is 1. Okay, so my derivative of this function is 4ax to the third 3bx squared plus 2cx plus d. And p prime of 0 is equal to 2, so that gets me d is equal to 2. So again, I'm building this polynomial down here. Okay, and I have an ax to the fourth plus bx to the third plus cx squared plus, now I have my d and I had my e. So we're going to continue building on this. My second derivative, that's a p. It's the problem. I'm trying to go too fast. So my second derivative is 12ax squared plus 6bx plus, and remember that was a 2c. So my second derivative at 0 is equal to 3. So we get c to equal 3/2. So I can now erase down here 3/2. Okay, so my third derivative is 24ax plus 6b. I'm sorry, the third derivative. This is the third derivative. I think I said fourth derivative, and I had notation for second derivative. That is equal to 4 when x equals 0. So b equals 4/6. And lastly, my fourth derivative is equal to 24a, and that equals 5. So a is going to equal 5 over 24. Okay, so that's our polynomial with these different values that it gave us. Now we're going to start with our fourth derivative and work backwards. So when I start with my fourth derivative, so my fourth derivative is equal to 5. When I integrate with respect to x, we get the third derivative. Now this may not be the best notation. Shh, don't tell anybody. We'll see, because I'm going to put this on YouTube. That'll be interesting. Okay, so solving for my third derivative, okay, plugging in this point, I get the formula for my third derivative to be 5x plus 4. Now, integrating this now with respect to x. Now I'm kind of, think about it as I'm going backwards. So I get my second derivative is equal to 5/2 x squared plus 4x plus another constant. I'm going to call it c sub 2. Solving for when my second derivative is equal to 0. I'm not going to have that 0 in there. I'm going to want that to go away. I plug in 0 for x using this point, and hopefully you see right away that the constant is going to be 3. Now what I'm going to do, again, I'm trying to go too fast because I want to get to the examples. I don't want it to be a super long video for you all. I'm not going to reduce any of these powers because I want us to see something. Again, using that value. Okay, now I'm going to integrate. I'm going to move my integration work, kind of separate it out, and hopefully I'll have enough room up at the very top. So I get my p of x function is equal to, oh no, I did something wrong. Oh no, I didn't. No, I didn't. 5 over 24 x to the 4th plus 4/6 x to the 3rd plus 3/2 x squared plus 2x plus my c sub 4. Again, plugging in this value. Hopefully you're recognizing something. Hopefully you're recognizing that this polynomial, whether I started with the derivative, whether if I started with an integrated back to get to my original or started with the original, we get the same polynomial that we had. It's the same polynomial that we had over here. Okay, so there's a really, really cool theorem, I think, that is kind of fun for the use of all of calculus. So Taylor series. So a Taylor series, we're going to take a non-polynomial function and approximate it to a polynomial. Okay. A Taylor series is, a fancy name is for that is called a Maclaurin series. Basically means our center is 0, and meaning that the center is 0. We're starting at 0 as kind of like our basis point. Okay. We started and we used the point 0 to get all these values. We use these points 0. Okay. Sometimes we're going to adjust that. So it's kind of fun. You have your initial condition plus f prime of 0 times x, f double prime of 0 over 2 factorial x squared, okay? And you just keep going till you get to whichever derivative order you need, okay? So this is a Taylor series of order n, okay? So the order means the highest exponent centered at 0. So let's talk about what this means. Okay, construct a fourth degree polynomial that matches the behavior of that by using successive derivatives of x. So I can take and I can find, I like to set up kind of like a little chart here. Since we're using 0, f of 0 is equal to 0. Now I find the derivative of this. Is equal to 1. I find my second derivative. the third derivative of x is 1 plus x to the negative third. The third derivative evaluated at 0 is equal to 2. The fourth derivative. The fourth derivative evaluated at 0 is going to be 6. So I have all of my coefficient values. So a Taylor polynomial, or a polynomial of order 4, is equal to my initial condition 0 plus first derivative times x plus my second derivative over 2 factorial, that's the order of the derivative, x squared, plus 2 over 3 factorial, because we're talking about the third derivative, plus 6 over 4 factorial. And I'm not going to do this with you guys. If we were doing this in class, I might have us pull out our calculators and graph that function in y1, graph this function in y2, and see how much it matches up and what x's it actually looks like it matches up for. And what could be this word that I'm going to keep using, the interval of convergence. Meaning, for what x's does this polynomial function line up with the actual function value? Okay, so what if we're not centered at 0? What if we are centered at a? Okay, it's the same thing, just you have x minus a. You've just shifted it x minus a. So the only thing you have to remember is you're just shifting it. If you think about it, if it was x minus 0, well, hey, that would get us what we just talked about. Okay, so a Taylor polynomial, okay, before we did a Maclaurin polynomial of order n, we get this is at x equals a. So our center basically is changed. We're changing where we're moving our graph, essentially. Okay, so I need a fourth degree Taylor polynomial for y equals cosine of x centered at x equals pi over 4. Okay, so get your derivatives. And get all these values. This is kind of the tedious part. I recommend that you write all of this down. And for me, it's just a matter of copying this from my notes. Hopefully you see where I'm getting all these values from. My third derivative is the sine of x. And then my fourth derivative is root of sine is the cosine of x. Remember, they repeat every 4. And I was just looking at this one. This one should be a positive root 2 over 2. Okay, so now I have my Taylor polynomial. You could have written a p polynomial if you wanted. Okay, take your initial value, and then the value of the first derivative, and that just so happens to be a negative, so I'm going to put a negative in there, x minus root 2 over 2 over 2 factorial. You're welcome to simplify that. Now I realize I made a mistake. I make the mistake that I make every year. This is my third year teaching the class. And I forgot to add in the pi over 4. What I was too worried about is I was worried about forgetting the over root 2 when I was thinking about this term. And now I move on to my third derivative, which is positive, so I have a root 2 over 2. Where I was talking about not forgetting, you don't have to simplify this, okay? But making it very clear to me, making your writing super clear, making it clear that I can read your writing. Because remember, yeah, I've gotten used to some of you that I've had for 2 years. I've gotten used to maybe some messy writing, but the people grading the AP test will not be used to your messy writing. Again, don't worry about simplifying this. And you can leave it like that. Okay, so that's our Taylor polynomial approximation. Okay, this is kind of similar to what you would find in an AP question. I've seen this on multiple versions of their test. So you have the derivative orders at 1. Okay, so I can't forget to write in x minus 1. I'm going to forget that, so don't yell at me. I'm going to try and remember. And I have these different values for the derivative. I don't know what the function is. I'm going to use this to write a Taylor polynomial centered at 1 and use that to approximate 1.1. So my Taylor series, or my Taylor polynomial, 3 plus 4. Oh, I didn't forget this time because I was worried about it. Again, don't worry about simplifying that, because remember, if you simplify and you make a mistake, they're not going to give you credit. Now from here, all it is plugging in 1.1 for all your x values. I'm not going to go through that algebra. I'm just going to show you guys what I got when I plugged this in my calculator. Okay, so that's what you would have for that example. Okay, some series that you have to know cold, some ones that I really, really want you to know, and I'm going to talk about one of them in specific here. Remember, this first one's a geometric. This one's just a geometric that bounces between a few things, okay? From the introductory activity that we did, we discovered sine, we discovered cosine, we discovered e to the x, okay? We derived arctangent by looking at this one, okay, and plugging in x squared and then taking the antiderivative. And then lastly, this one, ln of 1 plus x. I believe our book actually just uses ln of x. You can choose to memorize ln of x, or you can choose to memorize ln of 1 plus x and then just modify it. And we'll talk about how to modify it on the next slide, okay? But you're going to want to know all these. You're going to want to know, this is, over here, I have the interval of convergence. And remember, we did an activity in class to derive all of these. Okay, you could also technically derive all these from the processes that we talked about in this lesson. Okay, and all of these are centered at 0. So they're Maclaurin series. Our book calls these the elementary series. And actually, our books, and I spelled elementary wrong because I just looked at the time for recording this. Remember that, or realize that our book gives you guys a few more. These are the ones I want you to know, okay? This ln of 1 plus x, I think our book gives you ln of x. In a later video, I talk about ln of x. So I think that's the one I'm going to have you guys memorize, okay? But we can always adjust this one, and I'll show you guys how to do that in a minute. And actually, we did this one earlier in the video. Okay, last example. So write the first four terms in general term for the Maclaurin series for f of x equals cosine 2x. So what you could do is you could take the four derivatives if you wanted, okay? But if you realize that the approximation for cosine of x is this from that elementary series slide that I just gave you guys, and something I forgot to say on the last slide was you might want to go back and pause it and write all those down. I have given you guys a sheet, and hopefully with that sheet, okay, we've derived all of those as we've worked through a few things, a few different concepts with an activity that I do with you guys. So if we have cosine being this, okay, I need to do cosine of 2x. So notice the only thing that I changed. What I changed was I put in a 2x instead of an x. They went in the first four terms. So I have 1, 2, 3. Hopefully you see the pattern. And wherever I see an x, I'm going to put in a 2x. And again, you don't have to worry about simplifying that. Okay. And I don't like the equal signs there. I personally like the approximation. Okay. If it asks for the general form, I don't like the word form there. I like the word term. I'm annoyed I didn't see that yesterday when I was looking at these. So my general term is -1 to the n. Wherever I see an x, I put it in x squared. So wherever I see an x, I put in I'm sorry, not an x squared, a 2x. So that would be your general term, okay? And I want to use approximation symbols here because it's not exact, okay? Okay, so that is your introduction to Taylor polynomials and Maclaurin polynomials.